Welcome to AP Calculus, Chapter 4, Section 3. We're going to talk about derivatives of inverse trig functions today, and we've got some information about here that talks about when they're differentiable. It pretty much follows everything that's been said about when a function is differentiable. We also have a process for deriving our own, coming up with our own derivative formulas, and that was covered in class, so I'm a little tight on time constraints today. I may include that video later, but the first page of this, we're just supposed to build our own rules for these. And it's worth being able to do that. I'm not trying to discount that, but since it was done in class, I'm just going to use those rules. And then once we find the derivative for finding sine inverse of x, everything else that we know about derivatives applies, such as if I had 6x times sine inverse of x, it would just be a product rule with our new derivative rule for sine inverse, Okay, so what they show up here is on page 2 is our chain rules. So if u was x, then my derivative of sine of x is just 1 minus square root 1 minus x squared, because this would be dx on dx, and that would just be 1. But u, if it's a function of x, we just include the function here and then take the derivative of the function there, and oftentimes we'll just put that up in the numerator. But that is just the chain rule. We don't need special chain rules for trigonometric functions. They are exactly the same. We do have some less than, greater than 1 implications here, and that will just happen naturally unless we have a bad problem where we're like outside of the domain. For instance, sine inverse, there are restrictions on the values of u that we can put in there. The values that we can put in there would be the values that come out of sine, and since the graph of sine is limited in here, between -1 and 1, we can only put values between -1 and 1 in there. However, we also can't put the values where there's 1 in there, because if u happens to be 1, we're dividing by 0. Take a look at this. If sine's slope is horizontal right here, sine inverse's slope would be vertical. So u cannot be 1 as well. So those restrictions pretty well take care of themselves, or you'll come up with some weird algebraic type of error, division by 0 kind of thing. So anyway, here's our 6 rules. If it was just x, then we would just ignore the du dx's after that. Okay. So find the derivative. I think I'll leave this in view for us for at least starters here. We're going to need cosine derivative rule here. Find the derivative with respect to the appropriate variable. We're going to find the derivative. We're going to find dy dx, derivative of y with respect to x, or y prime in this case. But cosine inverse's derivative of x is -1 on square root of 1 minus, but we got a baby function. The baby function squared, my baby function is x squared, x to the 4th. Then times the inside function. There's our du dx. U is x squared. We're treating u as though it was x squared. And we just find the derivative of u. We could have done this way. We could have said negative, I'm going to come back to this. We could have said it's -1 on square root of 1 minus u squared times du dx. And then we could come back and put x squared in here. Okay? So I still need the baby function here times 2x. So we would typically wrap that up as -2x on square root 1 minus x to the 4th. dy dx equals. Okay? Maybe I'll do this one with u substitution and go through that process. That might help clear things up a little bit. But here's our sine derivative. Sine derivative is exactly like cosine derivative. This is kind of nice to know, except it's the opposite. Look at this. Tangent derivative, exactly like cotangent, but cotangent is the opposite again. And secant and cosecant, the same, except opposites. So we start to get kind of a feel maybe why, because when I started out in trigonometry, I thought, well, I learned that sine was opposite on hypotenuse, and then I learned that cosine was adjacent on hypotenuse, and I thought, well, why isn't why aren't they reciprocal? Maybe that's what the co should be about. Well, there's more to the co-function than that. And if you think about it, we're talking about inverse functions. At its most base level, what does an inverse function? It exchanges x and y. And if we're exchanging x and y, if sine is y on r, cosine is x on r. It exchanged the y and x. Well, not a real surprise then that we've got similar answers. If tangent is y on x, cotangent's x on y. Not a real surprise that we have similar results then, if we're just exchanging x and y's. Okay, so anyway, sine, if you need to take a look at it one more time, of course you can just look at here. This is cosine is negative 1 on, we had the minus there. So here's our sine rule we're about to use. I guess I'll just put that down here. It's 1 on square root 1 minus u squared. Let's do this with u substitution, just to practice. We're going to say u is square root of 2t, and we're going to treat this like y equals sine inverse of u. So that is dy dx. Well, that's easy. It's just this 1 on square root 1 minus u squared, but times du, in this case, would be du dx, du dt. We still have to take the derivative of u here. So du, I guess I'm going to go dy dt, du dt. Okay. Well, now if I substitute square root of 2t back in there, and this isn't something you have to be married to, but I just wanted to show it to you. I get 1 on square root of 1 minus u. If I replace 2t back, square root of 2t back in here, I get square root of 2t squared, 2t, times the derivative of u is the derivative of square root of 2t. I'm just going to write it this way. Square root of 2t. That's my inside function. So let's clean that up just a little bit. dy dt, we might want to think of that as 1 on square root 1 minus 2t. And maybe we want to think of, should have put the derivative symbol here, square root of 2t. We might want to think of that as 2t to the 1/2. We still have to find the derivative. And I get dy dt equals, chain rule, 1/2 times, leave the baby function alone, 2t, reduce the exponent to negative 1/2, times the inside derivative 2. Again, I'll refer to that guy as the heartbreaker a lot of times because that gets missed. All on square root 1 minus 2t, or dy dt equals, the 2's cancel, 2 and 1/2, excuse me, cancels, and I get square root of 2t on square root of 1 minus 2t. And it's tempting to try to think about doing some simplifying there. Be careful, I don't have any common factors. Okay, secant. I'm just going to put the derivative with respect to y. If it was just plain old secant of x. Secant of x's derivative equals, and I'm just getting this from above, and it's kind of a good discussion why we get this absolute value. That was on our previous discussion, but that was done in class. But I'm happy to create a video on that if it looks like that's necessary. So that's our derivative if we just had x here. So if you like the u substitution, you're going to see more of it. I'm going to do this without u substitution. So dy ds, careful, dy ds is this derivative. However, x is replaced by 2s plus 1. So I'm doing the substitution, just doing it in my head. That is 1 on absolute value 2s plus 1. Let's make sure our absolute values are bigger than our numbers. That way we don't end up treating it as a 1 or treating this as a 12. So it's absolute value of the baby function times square root of the baby function 2s plus 1 squared minus 1. Treat the baby function. I could put that times out here, but the derivative of the baby function is just 2. I could put 2 over 1 here, but it's going to get multiplied into that numerator. So I get dy dx equals 2 on. We ought to clean this up because I see out of this foiling I'm going to get a 1, cancel the 1. So I get absolute value 2s plus 1 times square root of, if I FOIL this, I'm going to get 4s squared. I'm going to get plus 2s's plus 2s's plus 4s. I'm going to get plus 1 minus 1. And sure enough, we got another step. I could factor a 4 out of this, take the square root of 4, 2, reduce that 2, and I end up with 1 on absolute value 2s plus 1 times square root of s squared plus 4. And once again, I went dy dx, but it's dy ds. We're taking derivative with respect to s. Okay, so let's move on here. Cosecant. I need to know cosecant's derivative, so I'm just going to jot that off to the side since we're new to this. Plain old cosecant inverse. Did I do that on the back page? I just said secant back here. I apologize. I'm sure some of you saw that. Secant inverse's derivative, of course. So let's go back. Excuse me while I fumble through this. Cosecant inverse's derivative, back from the front page, tells us cosecant inverse's derivative of x would be negative 1 on absolute value of x times square root of x squared minus 1. But it's not cosecant's derivative, or cosecant inverse of x, it's of x squared plus 1. So we have a baby function here. So y prime, or I guess I should go dy dx, it is dx this time, equals negative 1 on, if I was really clever here, I could already write this as negative 2x. I know I'm going to be taking the baby derivative out here after I'm done, but we'll do things in our normal order. Equals absolute value, not of x, of the function, x squared plus 1, absolute value, bigger than our 1, times square root of, not x, but the baby function, x squared plus 1 squared, minus 1. And once again, it looks like foiling is going to do me a world of good here. No, not a world of good, but it's going to do me some good. I'm going to get some canceling. But treat the baby. Here's my baby function, x squared plus 1. The derivative of that is 2x, as we said. Again, that could be put out here as 2x on 1. So anything good happen here? Let's see, we get negative 2x on absolute value x squared plus 1. Well, that's kind of interesting. We're going to come back to that one. Times square root of, let's see, if I FOIL this, I get an x squared squared, I get x to the 4th, I get a plus an x squared plus another x squared plus 2x squareds, I get a 1 times 1, 1 minus 1. dy dx equals negative 2x on absolute value x squared plus 1. Think about that one for a second. Factor out, can't really factor out simplify here. So I thought that I was going to be able to get something here. Well, you know what, I could factor out an x squared here, couldn't I? Factor out an x squared and I get x, square root of x squared x, this gives me x squared plus 2. Alright, so my 2's cancel, I got that. dy dx equals 2's cancel, negative x on, let's deal with So this x cancels this x. X squared plus 1. I got this absolute value around that. X squared is going to be at least 0 plus 1. So it would probably be nice to clean this up and just say that's x squared plus 1. Because that value is going to be positive times square root x squared plus 2. So once again, calculus, easy. Algebra, maybe our bigger challenge. Okay, let's take a look at E. E, I'm going to jot it down again here, this time right. Secant inverse of X, given on the previous page, basically, tells us that we end up with 1 on absolute value of X times square root of X squared minus 1. It's just like cosecant, except positive. So if we know one, we know the other, and the cos include the negative. All right, so secant of this function, dy dt. You could use a u substitution here. Dy dt, secant inverse, that becomes 1 on absolute value of 1 on t, my baby function, times square root of 1 on t squared minus 1 times, I'm just going to do this, 1 on t's derivative. Not going to try to be a hero and do 7 steps in one this time. Dy dt equals, let's take derivative of 1 on t. I'll just sidebar that one. 1 on t could be t to the negative first. Finding its derivative, I get negative 1 t to the negative second times 1 on. Now, they're telling me that for whatever reason, 0 is less than t is less than 1. If t is bigger than 0, the absolute values are no longer a player. This is just 1 on t. This becomes 1 on t squared minus 1. So if I shuffle things around and I bring these, let's just take care of this. Those can come to the bottom. Or in effect, I'm multiplying by t squared on t squared. When these come to the bottom and become t to the positive second, I get dy dt equals negative 1 on t squared times t, or 1 on t, just becomes t times square root 1 on t squared minus 1. If it drove you nuts that we had, or if the back of the book answer didn't have the fraction in here, how could we eliminate the fraction in here? We could multiply by square root of t squared on square root of t squared, which seems a little bit weird. Let's see what happens with that. I haven't prepped this problem, so maybe that's a good thing. I get negative square root of t squared is negative t, because t is bigger than 0. I don't have to do the plus or minus thing here. What do we get down on the bottom? I get t times square root of t squared times square root of 1 on t squared is 1 minus, but now I got the square root of t squared in there, and that's, I guess that's just a t though, so maybe we can deal with that. I don't know why I put that here. I've made a mess out of this, sorry. Dy dt equals negative t, that cancels this t, and I get negative 1 on square root, are you kidding me, 1 minus t. I guess that was worth it. Okay, cotangent inverse. May want to go back and look through that one, rewind that one, take a look. Cotangent inverse square root of t, I might want to immediately think of that as cotangent inverse of t to the 1/2, like this. And let's write out our cotangent formula here. I know it's going to be negative. Cotangent inverse x's derivative from our rules section. Cotangent inverse derivative is, there's our negative 1 on 1 plus u squared. Oh, that's kind of nice. A little simpler than our secant cosecant one. So if y equals this, then what am I going to do? dy, I'm going to think about it, dt. Derivative of y with respect to t becomes negative 1 on 1 plus. I would square this if this was x or t. But it's not at square root of t, so I square the square root of t, and I get t. Times the inside derivative. Well, the derivative of t to the 1/2 is 1/2 t to the negative 1/2 So I end up with dy dt, maybe don't end up, we'll see how this works. This is a denominator eventually with the 2, negative 1 times 1, negative 1 over, let's just change this guy for a second, 1 plus t, I've got to multiply that by the 2 and I've got to multiply that by a square root of t. So I end up with negative 1 on 2, maybe root t times 1 plus t. Root t times 1 plus t. dy dt. All right. Y equal, okay, now we got a mess going on here. Let's see what we got here. I got a product rule on S, dy ds. Product rule. I need the first function alone. I need the derivative of the second, but the second function could be thought of as 1 minus s squared to the 1/2. So that is 1/2 times 1 minus s squared to the negative 1/2. Treat the baby. Derivative of this is negative 2s. That is first. All I've done so far is first times derivative of second. I still need to finish the product rule with plus derivative of first. Well, that's nice. 1 times just plain second. Maybe I'll make that 1 minus s squared to the 1/2 for right now. Plus derivative of cosine inverse. Well, derivative of cosine inverse is nice. This is s. This isn't a chain rule. Derivative of cosine inverse s with respect to s is just negative 1 on square root 1 minus s squared. All right, let's see what cleans up here. 2's cancel. Negative, pair of s's. Negative s squared. I'm going to put this on, maybe I'll leave it to the 1/2 instead of making it square root. 1 minus s squared, I may regret that, but it's just another step. So I get this plus 1 minus s squared to the 1/2 minus, or plus negative 1, 1 on, I'm going to make this one 1 minus s squared to the 1/2, and all of a sudden I look at that and I'm like, common denominators, and wouldn't be too bad a deal to get common denominator here if I multiply this by another 1 minus s squared to the 1/2 on 1 minus s squared to the 1/2, I get negative s squared plus, take a look, this would be 1 minus s squared to the positive first minus 1 all on 1 minus s squared to the 1/2. What happens in the numerator here? I get a minus s squared minus an s squared, or I'm going to put that over here. I get a minus 2s squared. I get a 1 minus 1 all on the square root of 1 minus s squared. dy ds. Sorry, I shouldn't have slid that forward. Okay, so here's the deal. Once we know these derivative functions of cosine, sines, etc., we can just go ahead and use our previous rules. I have to stop at that point right there. There's a couple more. I'd be happy to take questions on these in class. This is going to turn into some algebra and trig issues that we're going to need to spend some time working with. So I will try to wrap these up, but that may not happen in the next day or two. Thanks for tuning in.